We have a, let's see, programming assignment 6 is due Thursday, right? Programming assignment 7 is due a week from Thursday. It's not posted to the course website yet, but we're actually going to deviate from the idea of building on the project that we've been working on the entire semester, and hopefully it'll be a little easier. What I want to do is make an implementation of Heap Sort and an implementation of Selection Sort. We'll talk about both today. And the assignment will be compare the runtimes. So make up an array and sort it using Heap Sort, and take the same array and sort it using, what did I say, Selection Sort. And use the system.currentTime millis that I used last class to try to compare hash map and tree map, which didn't really work out too well. But with Insertion Sort and, no, Selection Sort. Selection Sort and Heap Sort, we should get very obvious time differences, especially if you run the program on sizable arrays lots and lots of times. You can even use math.random to construct really, really large arrays really quickly. Just make sure that you, so both Heap Sort and Selection Sort are in-place sorting algorithms, so you don't have to create a new array. Make sure you make a copy of that array that you create if you're using math.random, so that the same array is used for both the input to Heap Sort and the input to the other one, Selection Sort. And so with that, we can talk about sorting. The book talks about 5 sorting algorithms. I forgot mine at home, so I have it on an iPad. Talks about insertion sort. No, talks about selection sort, insertion sort, merge sort, quick sort, heap sort, and then it briefly mentions that there are other sorting algorithms. We won't talk about any of those other sorting algorithms, but I do want to talk about one of the less efficient sorting algorithms that the book doesn't talk about. So in with the discussion of quadratic sorting algorithms, we also have something called bubble sort. And I like bubble sort because it's got a cool name, and it has kind of a cool drawing, illustration. So I don't know if I'll actually end up writing any code today. This is very much a conceptual lecture. The book has implementations of 99% of the code for all of these sorting algorithms, but the hard part is really the conceptualization. So we'll spend a bunch of time on that today. Just as an example array, I'm picking the one on page 616, which conveniently is in the discussion of selection sort. We're going to start with bubble sort, though. Of course, I pick markers that don't work. So let's rewrite that again. 10, 8, 6, 2, 16, 4, 18, 11, 14, 12. So the idea behind bubble sort the reason it's called bubble sort is that heavier elements bubble to the bottom and lighter elements bubble to the top. So here we'll talk about this as being our top, since smaller elements, which we'll equate with lighter, smaller elements usually end up at the beginning of an array. We'll sort in non-decreasing order. That's the standard way to sort arrays. So let's take a step back and talk about how no, let's do that second. First, we'll talk about bubble sort. So here's the lighter end. So this is, I did start the video, right? Yes. Okay, so this is the top, this is the lighter end, this is bottom, this is the heavier end. And this sorting algorithm is basically a double for loop algorithm. So for every element it's really not for every element in the array, it's for the number of elements in the array. It's just that's how many iterations it needs in order to work out. But the inner loop is more or less for every position in the array. So the idea is that we start with the entire array. The entire array is unsorted, and that'll become a theme as we talk about these sorting algorithms. We start out by treating the entire array as unsorted, and then pieces of it get sorted, and pieces of it are still unsorted, and we kind of go from there. So we want heavier elements to bubble to the top. No, to bubble to the bottom, and lighter elements to bubble to the top. We have two approaches that we can go with. Either focus on finding the moving smaller elements or moving larger elements. I'm going to start by moving larger elements. So gradually, eventually that means that after the first iteration, the largest element in the array will end up here. Then the next iteration, the next largest element will end up here, and so on and so forth. So gradually it's kind of like we're dropping a bunch of things in the water, and eventually the heavier things go down first, and even though that's not how gravity works, the heavier things go to the bottom, and the lighter things go successively on top of that. Yes? Bubble sort.
It sounds just like insertion sort.
We'll see very soon the difference. It is quite different from both selection sort and insertion sort. So the elemental operation in bubble sort is a swap of two elements right next to each other. So, and that's one way it differs from either of those. Insertion sort and selection sort, and we'll see that in a minute, they find a particular position and swap it with a known position. Bubble sort, it's just comparing pairs right next to each other. So since we're trying to get large elements to that direction, we'll start at this end and compare this pair. 8 is smaller than 10, so we do need to swap those, because 10 should be moving that way. So we end up with try to highlight the ones that have changed. 6, 2, 16, 4, 18, 11, 14. Okay, so the first iteration of the inner loop of the first iteration of the other. Look at this pair. 10 is greater than 6, so we need to change those two, swap those. So 6 and 10. 10 is also greater than 2. That's the next iteration of the inner loop. So So we get that. Now, these are in the right order, so this stops. 16 is now, that's a 10, not a 20. 16 is now the largest element of this pair, so we don't do anything there. The larger element is on the right. Here, the larger element is on the left, so we do need to swap them. This pair, we're okay. This pair, we're not okay. This pair, we're not okay. We do need to swap them. And here, we need to swap them as well. So it's just kind of convenient that every element in the original array moved somewhere else in the second iteration, or in the first iteration. That's not always going to be the case. Bubble sort is an algorithm that takes exactly the same amount of time to run no matter what order the elements are in, because you always look at each pair of elements, basically every possible combination of elements. So after the end of the first iteration, so this is first iteration, this part of the array is sorted. The heaviest element has bubbled to the bottom, and now we have a bunch of lighter elements. We have a bunch of unsorted elements, all of which are lighter than the element that bubbled all the way to the bottom. Let's see. So, second iteration. Second iteration. 8 and 6. Do I need to swap? Yes. 8 and 2. Do I need to swap? Eight and 10. 10 and 4. 10 and 16. 16 and 11. 16 and 14. And 16 and 12. Yes. So now we have one more element of the array sorted. And we can keep doing that over and over again. And so this is third iteration. 6 and 2 need to swap. So 2 goes over there. 8 and 6 and 8 do not need to swap, so that's good. 8 and 4 do need to swap. 8 and 10 not. 10 and 11 do not. 11 and 14 do not. 14 needs to go to the right of 12. And then, obviously, those last two elements don't change their positions. So, we're getting there. Okay, so fourth iteration. I guess I just started writing everything in orange. Oh well. So much for color coding. Okay, 2 and 6 are in the right order. 6 and 4 are not. 6 and 8 are. 8 and 10 are. 10 and 11 are. And yeah, all of that is good. So at this point, we know that we're done, but there's no quick way of determining that on a computer. Sure, we could go through and say basically what we're doing. Are these in the right order? Are these in the right order? But with bubble sort, we just don't swap if they're in the right order. And if they're in the wrong order, we do swap. And eventually we determine that we get 11 in the right spot, then we get 10 in the right spot, then we get 8 in the right spot. And eventually, the next iteration, our sorted area would go to there, the next iteration there, and so on and so forth. And eventually we have a smaller and smaller unsorted part, and the larger elements keep sinking to the bottom, bubbling to the bottom. Questions? Cool. Bubble sort is nice because it's relatively easy to conceptualize. It's also relatively easy to implement. Unfortunately, it is very slow. It will always have the same number of computations. It is always n squared. So there's an outer for loop that runs the same number of iterations as there are elements in the array, maybe off by 1. But essentially, however many elements are in the array, that's how many iterations of the outer loop you have. And then this inner set of iterations to check if these elements are in the right order and swap them if they're not. That goes basically incrementally fewer number of iterations. So the first iteration of the outer loop, it has n-1 comparisons. The next time it has n-2 comparisons. The next time n-3, and so on and so forth. But it's still directly proportional to n. So you basically have 2 for loops, n times n. You have quadratic time. So that was bubble sort. Now we'll talk about. I always get the names. I know which one I'm talking about, but I always get the names backwards. Selection sort. Selection sort is named selection sort because it does exactly that. It selects the next element that should go in a particular position in the array. Whereas insertion sort does the reverse. It finds the position that a given element should go into in the sorted array. So selection sort, in my opinion, is a lot easier to implement. Certainly fewer lines of code, fewer operations. Technically, depending on how you calculate it. So technically, insertion sort and selection sort are both quadratic. However, insertion sort has, you have to copy pieces of an array around to keep everything in order. You find a location in the array, but because there's no space there, you have to move a piece of the array somewhere else. Selection sort, you don't need to do that. Selection sort, just like bubble sort, has a sorted part of the array and an unsorted part of the array. Just like bubble sort, you can choose it to be at the beginning or at the end. If you choose it to be at the beginning, you're looking for the smallest element. If you choose it to be at the end, you're looking for the largest element. I usually choose it to be at the beginning and then look for the smallest element. So the first iteration, it's difficult to draw this one. So the first iteration, the entire array is unsorted. So I start at the beginning, assume that this is my smallest element, and then look through the rest of the array to prove myself wrong. So start out with that assumption. 10 is the smallest element in the array. We all know that it's not, but a computer doesn't know that. So assume that this is the smallest element in the array, and that its index is 0. So while we're going through this search, basically, we keep track of 2 things. We keep track of the minimum and something that's usually called argmin, the index of the minimum value. So initialize those to, we'll call this data sub 0, which in this case is 10, and the argument should be 0. So the index into the array, assuming this array is called data. That's our initialization step. Then we look through the rest of the array, and starting with 8, is 8 less than 10? Yes. So that means we found a new minimum. Out of the elements that we've looked at, this is the minimum element. And we change both what we have stored in min and in argument. So this is index 1, and its value is 8. Look at the next one. It is even smaller. So minimum is 6, and argument is 2. We keep going through the array, and then eventually we'll find that this is the smallest value in the array. Its value is 2, so eventually we'll have 2 stored in min, and its index is 3. So we'll have 3 stored in argument. So now we have an element of the index of the smallest element in the unsorted part of the array, and we put that at the beginning of the unsorted part of the array. So we know where the unsorted part of the array starts. Right now that's at index 0. This is index 3. So we swap them. So we end up with, I'm going to erase this so I can write the new array right below it. So we swap, there we go, that's easy. Okay, so we swap 10 and 2, and we end up with this array. And now, this part of the array is sorted. That's the smallest element. Now we'll go through the rest of the array, the unsorted part of the array, doing the exact same thing we did on the first iteration, and looking for the smallest element in that part of the array. So assume that 8 is the smallest element. 6 is smaller. Okay, now assume that 6 is the smallest element. 10 is not smaller, don't do anything. 16 is not smaller. 4 is smaller. Assume that that's the smallest element. And that's at index 5. And then we can look through the rest of the array, see that there's no smaller element than 4. So swap index is 5, and index 1 is at the beginning of the currently unsorted part of the array. So we swap those. So this is still sorted. This stays exactly the same. And we swap 4 and 8, and everything else stays the same. 10. Let's be consistent here. Let's draw that. Okay. What's the next swap I'm going to do? On the third iteration, what swap will I perform? Dion. Yes. Jack, what will I do this step? Right? Okay. So I should swap these two elements?
Yes.
Okay, Clark, what's next? Yes. I forgot to ask. Can you see the board today? Okay. Since the colors are a little more vibrant.
More vibrant, but shades of green and red from colors and colors.
I'm sorry?
Shades of green and red are colors and colors.
Sorry, I picked the markers
It's better than
had available to me.
Green,
Better than green? Okay. And Lynn, what's the next swap I should perform?
16.
Yes. Yeah, okay. So 2, 4, 6, 8, 10, 11, 18, 16, 15. And at this point, I'm running out of space. So we'll stop there. Everybody get the idea of this? So eventually let's see, the next swap we do would be 18 and 12. And then 16 and 14, and then everything else is in order. So we still have approximately n iterations, and within each of those iterations, we have to do a linear search of the unsorted part of the array for the smallest element. So we know that linear search it's called linear search because it runs in linear time. So if we have n elements, the worst possible runtime it could have is n. We have to go look through all n elements before we find the one we're looking for. And in fact, because we're looking for the smallest, not just a particular element, we always have to go through all n elements because we don't know where that smallest element is going to occur. So n iterations, each performing n operations inside of them, that's n times n, which is n squared. So it's also quadratic. Questions on selection sort? Cool. Dion, did I talk about insertion sort in Visual Basic? Okay. Do you recall what was different about insertion sort and how it worked? Okay. So insertion sort is basically the reverse of selection sort. Instead of picking the smallest element, we look at the next element in the unsorted part of the array, figure out where it should go in the sorted part of the array. So in the case of this, we have 10 elements in our unsorted array and 0 elements in the sorted part of our array. So we can look at 10, and an array of size 1 is by definition sorted. So we move 10 to the first position and only position of our sorted part of the array. So really, there's no change. So we can start out assuming that our initial case is there is one element in a sorted part of an array. It is an element by itself, so it's by definition sorted. And then everything else is unsorted. So look at the element at index 1 and find out where that goes. In this case, it has to go before 10. So that means we have to shift everything over so that we can put 8 there. And now we have 2 elements in the sorted part of our array, and everything else is unsorted. The next element is 6. So where should that go? When? No, we're not. The only element that we're concerned about, so we can actually forget that all of these elements exist. We're only concerned with the first element in the unsorted part and the elements in the sorted part of the array. We don't want to switch it with 8 because these elements are already sorted. We don't want to mess with that order. So everything on the left-hand side should stay in the same order. We're inserting this element somewhere. We can either insert it here, here, or here. Those are our options. Right. So that means that both of these elements need to shift over 1. So we end up with a 6 here, an 8 here, a 10 here, and then the next element is 2. So the next iteration, Dion, where should the 2 go? Yes. So 2, 6, 8, 10, and what's next? 16. Jack, where should the 16 go?
So my glasses are dirty, so it's kind of hard to see them.
2, 6, 8, 10, 16.
Seems fine where it is.
Yes. Okay, so no change. So
10 is like a 16, that's why I look for it.
I'll try to draw zeros like that, if I can remember. And 16, and what's next? 4. Clark, where should the 4 go? Yes, so all of this needs to move over. And 2, 4, wow, 4, 6, 10, and so on and so forth. And eventually we get, what's next? 18. That's okay. 11 would go here. 14 would end up here, and then 12 would end up here. A lot of stuff going on right there. So it's a lot messier. In general, I don't like copying arrays if I can avoid it. And since insertion sort is no better than selection sort, might as well use selection sort. So all 3 of those sorting techniques are quadratic. This one, best case might be slightly better, and as weird as it seems, its best case is actually operating on a reverse sorted array. So that means that the biggest element is at the beginning, the smallest element is at the end. Because what is it looking for? It's really looking for the next element, given a particular element, it's looking for the next element in the sorted part of the array that is larger than it, and then placing it before. So if this array is completely reverse sorted, I have a simple example of that. 5, 4, 3, 2, 1. So there's our initial state. We're looking for where 4 should go. That's easy. It should go at the beginning because the first element is larger than it. So we end up with 4 and 5. Where should 3 go? Before that. Where should 2 go? before that. And finally, you have a fully sorted array. And then really the bottleneck is copying the array, pieces of the array around, moving things down. And its worst case runtime is a fully sorted array. Because besides being what we would call inefficient, it also needs to look at the most number of places. So if we start out with 1, 2, 3, 4, 5, where is 2 going to go? Well, it's not going to go before 1, and that's the end of our sorted part. So it's going to go there next. We don't actually have to move anything, but we still have to look through all one element. The next iteration, 3 is going to go not before 1, not before 2, so it has to go after 2. So you look through still all the elements just to find that 3 didn't have to move, and so on and so forth. So that gets it very close to being completely quadratic. If n in the n squared quadratic runtime idea were a specific amount of time, it's not really a physical amount of time, it's a theoretical amount of time, that would be pretty close to how long it would take for insertion sort to run. And that's really what differentiates within a particular class of runtimes. Quadratic. What we'll see next is n log n, I believe. Within those comparative runtimes, the thing that differentiates different algorithms is assumptions you can make about the data. So if you can assume that the data is mostly sorted, selection sort if you can assume that the data is mostly reverse sorted, insertion sort is really good. If you can assume that the data is mostly sorted the way you want it to be, then selection sort is all right. Bubble sort is terrible no matter how you look at it. It always takes the same amount of operations. So all 3 of those sorting algorithms are what are called in-place sorts, which means that you don't need to allocate extra space in order to perform the sort. You can use, there's nothing preventing you from doing that, but you can use the same array to store both a sorted part of your data and an unsorted part of your data. So there's no really no overhead in terms of data storage. They are also another term called stable, which means that if you have 2 equivalent elements, say 2 4s in the same array, this one will always appear in the sorted version before this one. So this is always first and this is always second. When you're dealing with ints, that's not significant because an int is an int is an int. 4 is exactly the same as any other 4. However, when you're dealing with more complicated data structures, say if you're sorting objects on a particular property of that object, or dictionaries, or maps, I guess Java calls them, that comes into play. I guess they don't necessarily permit multiple keys identical keys, multiple entries that both have the same key. But if you have some data structure that does allow this 4 to point to hello somehow, and this forwards point to world, a stable sort will always sort the 4 that's connected with hello before the 4 that's connected with world. That's stability. And in some sorting algorithms, specific care is taken to ensure that it stays stable. There are some sorting algorithms that really don't care. And depending on how you implement a specific algorithm, you can make it not stable. For instance, if you did insertion sort and started looking from that dividing line, but kept moving that dividing line one element to the right, but instead of searching the sorted part of the array from the beginning, you started searching from the end and tried to find the next element that was the first element that was less than the element you're trying to place, then it would not be stable. The first 4 you encountered would go somewhere in the array. The second 4 you encountered would end up before that 4, which is not the original order. Okay, so quadratic sorting algorithms. Next, we talk about n log n sorting algorithms. And the first one that the book talks about is merge sort. The basic idea behind merge sort is that we split a given array in half, sort the smaller arrays, and then merge the sorted arrays back together. So it doesn't matter. It ends up that it doesn't matter how many elements are in either array. We picked the middle because it basically, if we look at the series of method calls as a tree structure.
Oh, no, I mean like an odd number, like if you only have like 5 values.
Right. Yeah. It doesn't matter if one side, in that case, you end up with one small array that has 3 values and one smaller array that has 2 values. The algorithm works exactly the same. The only reason that when we describe it, we talk about splitting it down the middle is we want, basically, if we look at all the method calls as a tree structure and look at the call tree, how many recursive calls there are, which invocation of the method calls which other invocation of the method, it ends up looking like a balanced tree. So we start out with an array that's like that, and we end up with a smaller array and smaller array, and then we end up with an even smaller array and an even smaller array. And that's all still balanced. But if we didn't pick an element right in the middle, or if we didn't divide it down the middle, we divided it somewhere up here, we'd end up with basically that, and this would be larger. And that would split into, I don't know, let's say we do something ridiculous like that. And then we can split that into smaller arrays. And, well, those don't add up to the size. Something like that, and that's not balanced at all. So that really, we end up getting a runtime that's not n log n. It approaches linear, which is bad. We're trying to stay away from, or no, it approaches quadratic, rather. We're trying to stay as far away from quadratic as we possibly can. Try to take shortcuts, which this divide and conquer technique does very well. And it's this technique that allows us to perform very quick searches through trees. because we don't have to look through the entire set of data points. We figure out which side of a tree a particular data point is on and only deal with that tree. We've cut our search space in half. The next time we decide which tree to go down, we've cut that next smaller search space in half, which is how we end up with the logarithm in there. It's actually a log base 2 for a binary tree, for instance. For anything we divide into two pieces, two smaller search spaces, or in this case, I guess we can call them sort spaces, it's log 2. So with this array, we have 10 elements, I think. So we divide this, and then we can call, it's, again, a recursive algorithm. So it's basically, when we call merge sort on a large array, that calls merge sort on two smaller arrays, which each of those invocations calls merge sort on two even smaller arrays. And eventually, our recursion ends when we have an array of size 1. Or 0, I guess. If we have an array of size 0, we don't do anything. If we have an array of size 1, that array is sorted. So here we can divide this into 10, 8, 6 to 16. Let's divide it there. Now, let's follow normal rules of Java division. Right? So length of this is 5 divided by 2. That gives us 2. So let's say that index that it gives us is this first index of the second half of the array. So these are our two pieces. And now we sort this. End up with 10 and 8. This is an area where you can have different philosophical debates on what you want the base case of the recursion to be. Do you want to divide this array into two smaller parts, each of which has a single element in it, and then realize that you can't do anything with this single element, return, and then do the merge? Or just say, oh, I have two elements, let's see what order they need to go in. So let's do the second approach. Oh, I have two elements, what order should they go in? This is not the right order. Let's swap them. So by the time that call returns, that piece of the array is that. So let's continue this down here. So this gives us 6, 2, and 16. That's larger than two elements, so we'll split it here. This doesn't do anything. This, we have two elements, so we should, those are in the right order, so we don't need to do anything. So on this end, this side, we've reached our end condition. And we can start, we return from this recursive call, and now we're in this context. So we have a 6, and then an array of 2 and 16. Or an array with 6 in it, and another array with 2 and 16 in it. So now we have to deal with this merging part. And the merge algorithm is really kind of like zipping a zipper. Basically, we start with, we have two arrays, so, and I'm going to draw them going up. So here's array number 1, and here's array number 2. It's 2 and 16. And like I said, it's like a zipper. So we feed, let's see if I can draw a zipper. So right, so here's teeth. And when it comes out the other end, it's all zipped together. And eventually we know that we want to come out with 2, 6, 16. That's the right order. So the way we handle that is start by pointing to the beginning of each array. Pick the smaller element. So compare these two elements. Pick the smaller one, and that goes in to that goes into the output. And whichever array that piece of data came from, we increment that pointer by 1. So 2 goes into our output. And we advance this pointer. You can store that as the index into the array. So you might have, I don't know, left IDX and right IDX. So at this point I've taken 2 off, so now it equals 1 and points there. Now I do this comparison, and I see that 6 is the smaller of the 2. So 6 goes into the output. And we advance this pointer so that it points to 1. The other thing that I should be checking while I'm doing this is to see if either of those pointers are beyond the edge of their respective array. So now that left IDX is 1, there is no left data 1 because there is only one element in that array. So if I tried to use that in a comparison, it would array out of bounds, etc. That'd be bad. So before I try to compare values at these indexes, I check to make sure that neither of these indexes is outside of the bounds of the array. In this case it is. So it's outside of the bounds of this array, but this index is still inside the bounds of this array, which means that I still have data in this array that hasn't been added to the output. So I just copy the remaining parts of that array into the output. So at this point we can now ask a question. Is this sorting algorithm an in-place sort? This should be a big giveaway as to the answer. The answer is no. Merge sort is not an in-place sort because not generally an in-place sort. You could implement it as an in-place sort, I think. It'd be messy. It'd be really messy. In general, it's not implemented as an in-place sort because while these two arrays are actually really two pieces of the same array, the elements, each element is usually copied to an output array, and that's what gets returned by merge sort. So usually instead of taking in an array as an argument and not spitting out anything, just having the side effect of sorting that array, merge sort usually takes in an array and returns a different array. So that means that we're done here. We can chop this off and say that the return value of that is 2, 6, 16. Which means that returns back up here. And we can replace that with 2, 6, 16. And 8 and 10 already has returned. We've done that. So we have 8 and 10. Now we have to do the same merging procedure that we just did on the subproblem. Out of 8 and 2, what needs to come first? 2. So I'll write it up here. 2. And I say it would be messy because if I choose that one, now I have to shift this array over, and that's bad. That messes with numbers. So the next thing is 6. The next thing, so cross those off. The next thing is 8. Next is 10, and 10, and then next is 16, because it'll be on the end of that array. And we can lop all this up. And we can do the same thing from the other side. So 4 and 18 stays in the same order. 11, 14, 12, divide here. 11 starts out being good. 14 and 12 need to be switched. 11, 12, and 14 is in the right order. And then we need to order all this, and it ends up that 4 goes first. Let's see, 11, 12, 14 goes next, and then 18 comes last. And now the big merge, which 2 and 4, 2 comes first. 6 and 4, 4 comes first. 6 and 11, 6 comes first. 8 and 11, 8 comes first. That is a 6. 10 and 11, 10 comes first. 16 and 11, 11 comes first. 12 and 16, 12 comes first. 14 and 16, 14 comes first. 16 and 18, 16. And then 18 is the only thing left over. So we have a fully sorted array. Yes?
So you basically just compared like each one until they fit into the sorted array?
Right. So it's kind of a advancing pointers, dancing pointers, competing. I don't know. You could probably come up with some metaphor for it. But you start out with some sort of pointer pointing to the beginnings of the array. Compare those elements. Whichever one is smaller, you take that piece of data, put it in the next slot in your output array, and advance the respective point. Compare those two elements. Pick the smallest one and advance that point. Compare those two elements. Pick the smallest element, advance that point. Do the same thing with the new positions. Back. And again. And then now it changes. Still this array. And now I'm past the end of one of the arrays. One of the pointers is past the end of its array. So I just take the remainder of the rest of the array. The remainder of the other array and tack that onto the end of my output array. And this becomes my output, my return value. Okay. Other questions on merge sort? Yes. That is determined by how big the array is that's passed in. So it's same way you determine how any other recursion ends. You have a base case and an approach. Our approach is split this array and call myself on both pieces. So call merge sort on piece number 1 and call merge sort on piece number 2. My base case is the way we did it is the size of the array that's passed in 2 elements. So is in array dot length 2 or smaller. If it's 2, then I make sure they're in the right order. If they're not in the right order, I swap them and return that. If there's only 1 element in the array that I passed, I just return that element. An array of 1 element is by definition sorted. And if I'm passed an array that doesn't have any elements in it, which in theory should never happen. We shouldn't ever end up dividing an array into an array of 0 elements and an array of any other number of elements, because our base cases prevent that. If we have an array of 0 elements, we return an array of 0 elements. An array of 0 elements is also by definition sorted. Doesn't make any sense, but it's defined to be that way. Okay. Moving onward, next is quicksort. And this quicksort, in the general case, is the quickest sorting algorithm out there, without making any other assumptions about the data. Its worst case is no better than merge sort. Its worst case is n log n, which is still pretty good. But in practice, on completely random data, it ends up getting quicker empirical runtimes. So it ends up outperforming its theoretical runtime. Just because it's very hard to give, on data that occurs in the real world, it's very hard to give quicksort bad data that it operates horribly on. And that's why it's called quicksort, because it's pretty good. So, using the same array, the basic idea of quicksort is that we pick a pivot point and divide the array into two smaller arrays. One array that contains all elements less than that pivot point, and one array that contains all elements greater than that pivot point. Do the same thing again, until we reach a base case. So it is also a recursive algorithm. And our base cases are exactly the same as with merge sort. If we have an array of 2 elements, make sure they're in the right order. If they're not in the right order, swap them. If we have an array of 1 element, it is by definition sorted. That's okay. And if we have an array of 0 elements, it is also by definition sorted, but we should never actually get that. Quicksort, unlike merge sort, is in place. And I'll actually demonstrate it in place. In general, sorting algorithms are easier to implement when you don't treat them as in place, but in place has a lot of advantages on its own, and they're really not that much trickier. So there's kind of an arbitrary part of quicksort, and that is what to choose as the pivot point. You could choose an element somewhere in the middle. For instance, in terms of this array, that would be absolutely terrible. That would be an absolutely terrible choice because most of the elements in this array are larger than 4. The computer has no way of knowing this, but we can tell it. In general, it's arbitrarily chosen to be the first element in the array. So basically, we construct, I'll draw it not in place first, and then I'll show how to do this as an in place sort. So here's 10 is our pivot point. Then we could go through the rest of the array and determine what's bigger and what's smaller. So here's our bigger, and smaller. Someone tell me what time it is? 2:44? Okay. So, bigger elements go here, smaller elements go here. 8 is smaller than 10, 8 goes here. 6 is smaller than 10, 6 goes here. 2 is smaller than 10, goes here. 16 is larger, goes in the bigger array. 4, smaller. 18, bigger. 11, bigger. 14, bigger. 12, also bigger. And conveniently, this pivot point turns out to be a pretty decent pivot point. Because the bigger array and the smaller array are approximately the same size. And we can perform that on each of these arrays as well and go further down our recursion tree. So, sure, let's do that. Here we can pick a pivot point of 16, and we end up with, so 16 is our pivot point. A bigger array has 18 in it, and then 11, 14, 12. Are in the smaller array. This is an array with one element in it. It is by definition sorted. We don't need to go any further. Here we'll go down and pick 11 as the pivot point, which is an absolutely terrible pivot point. There's nothing in our smaller array, but in our bigger array, we have 14 and 12. This has two elements in it, so we just need to make sure those two elements are sorted by swapping them. So we get 12 and 14. And then we can start with the reassembly. And the reassembly goes as follows. Since we've solved the subproblem of sorting all elements smaller than the pivot point, we can assume that array is sorted. Same thing with the bigger array. So we have a sorted array of things smaller than a pivot point, the pivot point, and then a sorted array of things bigger than the pivot point, which means we can reassemble this array by taking the smaller array, then the pivot point, then the larger array, and everything should still be sorted. So here, we have no smaller array. We have a pivot point and a bigger array. So we can assemble those together. We get 11, 12, 14. I should actually put that here. So 11, 12, 14. And then we can do the same thing here and reassemble. So smaller array, pivot point, bigger array. So we copy that in place here. 11, 12, 14, 16, 18. Right? And we can do the same thing that we did with the bigger array with the smaller array. So pick 8 as the pivot point. So we have 8. We have nothing in the bigger array. So empty set. And 6, 2, 4. That's bigger than 2 elements, so pick a pivot point of 6. Still absolutely terrible. Nothing in the bigger array. In the smaller array, we have 2 and 4. Those are in the right order, so now we can reassemble. So smaller array, pivot point, bigger array. So we end up with 2, 4, 6 here. Smaller array, pivot point, bigger array, so we end up with 2, 4, 6, 8. And we can do the same thing at the top level as well. Take our smaller array, then our pivot point, then our bigger array. So 2, 4, 6, 8, 10, 11, 12, 14, 16, 18. And we have our sorted array. Questions on quicksort? I realize I went through that really quickly. And it's not just because I ran through it. It really does go that quickly. I didn't have to think about much in terms of what elements were bigger than what other elements. All I have to do is put big elements in a big element area, small elements in a small element area, and then repeat the process on each of those smaller problems. Now, the in-place version of this kind of plays clever games. So we pick this as our pivot point. And instead of starting from here and then sorting things out into are they bigger or are they smaller, we actually treat this as one giant array. Have a pointer here and a pointer here that start going toward each other. And when they cross over, we know we've looked at every element. And the significance of those pointers is one is looking for really those elements that are bigger that shouldn't be on this side, and elements that are smaller that shouldn't be on this side. So we can go through here. 8 is smaller than 10, 6 is smaller than 10, 2 is smaller than 10, 16 is not smaller than 10. This is an element that we need to put onto that side somewhere over there, in theory. It should be somewhere like that. 12 is larger than 10, that's okay. 14 is larger than 10, that's okay. 11 is larger than 10, that's okay. 18 is larger than 10, that's okay. 4 is not larger than 10, that's not okay. So we found two elements, one element on the smaller side that needs to go to the larger side, one element on the larger side that needs to go to the smaller side. So we can swap them. And we keep moving our pointers. So then we go back to the smaller side. We found an element that is we think it's on the smaller side that should be on the larger side. But when we move our larger side pointer and find the next one, we find that the pointers have actually crossed over each other. That's our termination condition. We know that smaller things are on the left side and larger things are on the right side, and there's no larger things mixed in with the smaller things, or no smaller things mixed in with the larger things. And that means that that point, that crossover point there, is where the pivot point needs to go. Now, there's nothing that says this 4 needs to be in this place respective with this 2, this 6, and this 8. So in order to put the pivot point in between the 4 and the 16, we can just take this element here to the left of the split and swap it with the element we're using as the pivot point. So we end up with 4, 8, 6, 2, 10, 16, 18, 11, 14, 12. So now we have our pivot here. This is the set of smaller elements. This is the set of larger elements. And now we can do the recursive calls. Call the same sorting algorithm on this piece and on this piece. And because the array is already it's already an array, we don't have to do any reconstruction. As long as something sorts this array in place and something sorts this array in place, we're done. That's the last thing we have to do. Make those recursive calls, and when they return, the array is sorted. Questions? Okay, perfect timing. It's break time. I'm not going to specifically talk about heap sort in class. The book talks about heap sort, vaguely how it's implemented. We talked about how to construct a heap, how to take an array and turn it into a heap, with the heapification downward and heapification upward, all that good stuff. And we basically, when I was talking about heaps, I talked briefly, kind of alluded to how to perform a heap sort. having a heap means that the largest element, assuming it's a max heap, the largest element is on top. So you can easily take that off, put it somewhere else, and say that's the largest element in my array. Reheapify the remaining heap, and then the root that comes out of that is the next largest element. In heap sort, it can actually be an in-place sort because you can implement a heap on top of an array. It's very easy to do that. That's what we did in class. And if we treat the first large part of the array and eventually getting smaller part of the array as the heap, and have some sorted part of the array at the end that is no longer part of the heap, we can do essentially essentially how the remove method works. So instead of taking an element off and sticking it somewhere else, and taking the element at the end, making it the root, and then reheapifying downward, we can swap the element at the end and the element at the beginning, which means swapping the very last leaf node with the root node. The root node is the largest element in this array, so it ends up at the back, which is where it belongs in a sorted array. And this smaller element goes to the beginning. We reheapify downward, treating only the unsorted part of the array as the heap, and repeat the process. And that's basically it. Alright, so break, and then you're welcome to ask me questions about programming assignment 6. Programming assignment 6 will be the last programming assignment that deals with the interpreter stuff. At the end of programming assignment 6, you'll be able to run the print 1 to 10 program. And it should actually loop through everything. We're implementing jumps in this one, I believe. All right, cool.